Hello everyone. Before I begin this presentation, let me introduce myself. I am Zakaria. I am a PhD student from Faculty of Sciences and Technology of Beni Mellal. The subject of our presentation is presenting a modern control scheme for a solar pumping system based on asynchronous motor. This presentation includes four main parts. In the introduction section, we will cite the main components used in solar pumping system. In section number 2, we will briefly discuss the proposed control strategies. Finally, simulation results and analysis are reported to section number 3, followed by general conclusions. In the pumping system, there are two main parts, the DC part or the photovoltaic part and the AC part or the motor pump side. First of all, let us focus on the DC part. The photovoltaic array is the main component in the DC part. For a two-stage solar pumping system, the boost converter is used for maximum power point tracking. Now, we would like to take a look into AC part, in which the three-phase inverter is used to drive the induction motor. The centrifugal pump and the induction motor is the fourth part of our system. This is the block diagram of the entire pumping system, which combines both AC and DC parts. As a reminder, the DC part contains solar panels and the boost converter, and the AC part consists of three-phase inverter and the motor pump. That's all I have to say about the circuit description. In the next section, we will present the proposed control scheme. This flowchart shows you the conventional perturb and observe algorithm based on voltage perturbation for extracting the maximum power. The perturb and observe algorithm generate the reference photovoltaic voltage VPV. Then, the generated voltage is regulated with the sliding mode controller. For the control of the three-phase inverter, there are two controllers involved. The first one is the fuzzy logic controller, which regulates the DC bus voltage by generating the appropriate reference speed omega m. The predictive torque control is the second controller, which regulates the speed of the induction motor previously generated. First, let us focus on the DC bus voltage regulator. To ensure safe operation of water pumping system, the induction motor should consume the full energy provided by photovoltaic panels. Therefore, the motor speed should vary proportionally to the photovoltaic power. To achieve that, the maximum reference speed omega-1 is calculated with the following equation. However, the operation with the speed omega-1 does not guarantee the stability of the DC bus voltage. Therefore, the FLC block add the speed omega-2 to adjust the speed omega-1 until the DC bus voltage is regulated. The obtained reference speed omega-m is sent to the predictive controller. The predictive torque controller consists of three blocks. The block observer estimates the torque and the flux. The prediction block predicts the behavior of the torque and the stator flux. These variables will be used to construct a cost function in the minimization block. The constructed cost function is minimized with an optimization algorithm to provide the optimal switching action of the inverter. After describing the proposed control strategies, the pumping system is simulated using MATLAB simulating software. Figure A shows the applied profile of the irradiance. It is obvious from Figure B that the photovoltaic power follows the dynamic of the irradiance successfully. Figure number 9 describes the behavior of the DC bus voltage. The fuzzy logic controller disables the fluctuation of the DC bus voltage due to the change of the power. The regulation of the DC bus voltage guarantees safe operation of the motor. Figure number 10 presents the response of the speed. It confirms that the motor turns proportionally to the extracted photovoltaic power. This proves that the motor converts the full photovoltaic power into a mechanical power. We would like to conclude today's presentation with the strengths and the weaknesses of the proposed work. The results show that the system performs with good performances such as the DC bus voltage is well regulated, which prevents the motor from damage. The PTC showed robust control of the induction motor. However, The proposed control strategy still presents some drawbacks, such as the predictive torque control strongly dependent on the motor parameters. Secondly, the implementation of the FLC block is complex and requires high-performance processors. That's all about today's presentation, and thank you for your kind attention.